First thing we're going to do today is verify that the f function and the g function given are inverse functions. And there's this little statement that's not quite finished. Functions f and g are inverses of each other, provided that f of, I'm writing it wrong, that f of g of x, hey pen work, there we go, f of g of x must equal x. So if we do f of g of x and it simplifies down to just a plain ordinary x, that means everything that was done to x in one of the functions is undone by the other function because they are inverses of each other. So in number 4, our f function is 1/3 of x minus 1, and our g function is 3x plus 3. We need to do f of g of x. The f function is 1/3. We take that x out and put parentheses in its place, minus 1. And that entire g function is going to get put inside those parentheses. Okay, let's distribute. What is 1/3 times 3x? 1x. 1/3 times 3 is 1, and then we have minus 1. What is 1 minus 1? 0. So this becomes simply x. And we have thus verified that f and g are inverses. They undo each other perfectly. Cool thing about inverses is that you can do g of f of x and you would still get the same thing. Normally f of g of x and g of f of x aren't the same thing, but in the case of inverses, they are. All right, let's try the next one. Our f function is 3x cubed plus 1. Our g function is the cube root of x minus 1 over 3. And you might be able to already see in here how these are already going to be inverses. The first one has x cubed, the other one has the cube root. One of them has 3 times, the other one has divided by 3. One of them has plus 1, the other one has a minus 1. So everything that is being done in one of them is being undone in the other one. But they want us to verify by doing f of g of x. F of x is 3 times something cubed plus 1. We put the entire g of x function inside there. We can't distribute yet. The first thing that we need to do is cube the parentheses. Inside the parentheses, it is a cube root. What happens when you put a cube and a cube root together? They cancel. So we have 3 times x minus 1 over 3 plus 1. Do you see anything else that cancels? Times 3 divided by 3, those are going to cancel, leaving us with x minus 1 plus 1, which is x. So we now know that f and g are inverses. Neat. At the beginning of the school year and in Algebra 1, we talked about whether or not things were functions. And we did this thing called the vertical line test. So if I have a parabola and I put vertical lines through this parabola, each vertical line only touches one point at a time, so that parabola is considered to be a function. The definition of the function is that each x value can only have one y value assigned to it. So you can't have repeated x's. Like you can't have the points 2, 4 and the point 2, 7, because then it would not be considered a function. When we find, or like here, this example, if I've got a circle Is a circle considered a function? No, this is not a function because it does not pass the vertical line test. With inverses, we are actually reflecting this graph over a diagonal line and turning it on its side. So if I take this parabola and reflect it, I'm going to totally redraw it. If I reflect it, it's going to end up looking like this sideways C shape. Would that sideways C shape pass the vertical line test? No. So the inverse is not a function. Is there a way to figure that out without having to graph the inverse? That's where we look at the horizontal line test. If a horizontal line does not touch more than one point, then the inverse is going to be a function. So for each of these, we are going to graph the function shown and then decide, would the inverse be a function? If we reflected that over, would that new graph be a function or not? Do you remember how to graph y equals 3x minus 2? Yeah. Start at -2 on the y-axis. Use a slope of 3, up 3 over 1. Okay. All three of these are considered to be functions because they're using function notation. They would not use function notation with something that wasn't a function. So this does pass the vertical line test. It is a function. If we use horizontal lines, does this pass the horizontal line test? Yes. So F inverse, or you could just write the inverse, is a function. You can write f -1 to mean the inverse of the f function that we just drew. Okay. This next one is a parabola. I'm going to help you with the graph, and on your worksheet, I'm going to help you with the first part of the graph. X squared plus 1 starts up 1 on the y-axis. It has another point that is right 1 and up 1 from that vertex, and that point is also reflected over on the other side. Then from the vertex, if you go right 2 and up 4, that's the point 2, 5, and the point -2, 5. So there's our parabola. And we kind of already talked about this. If we reflected this over, instead of a U shape, it would make a C shape, and that C shape would not be a function. But we can see that right here, if we do the horizontal line test, we touch 2 points. So that means the inverse is not going to be a function. Okay, do you remember what the graph for number 11 is going to look like? Absolute value is a V shape. This one starts down 3. And it is the perfect V that goes up 1, out 1 from that vertex. Okay, this absolute value function is a function. Will its inverse be a function? No. F -1 is not a function. Because if we put a horizontal line through here, we touch 2 points. Okay, here is your worksheet for today. Number 1 is just the simple absolute value that starts at 0, 0 and has basically a slope of 1, so it creates that V, up 1, out 1 on both sides. Okay. I think that you can do number 2 on your own. That's just graphing a line. Number 3 is a parabola that starts down 1 on the y-axis. And do you see this piece right here? This is saying it wants the positive x values of this parabola. It only wants the right side of the parabola. So from this point, go right 1, up 1. And then from the original point, also go right 2, up 4. That is the chunk of the parabola that they want you to consider. So it's just the right half of that U shape. Number 4 and number 5, you are verifying that they are inverse functions. Remember, that means that you need to do f of g of x, and your goal is basically to make them both, like to make it equal x once you've simplified it. At the bottom, 6 through 8, it's finding the inverses. That's what we did yesterday, so that's more practice like yesterday. Same thing with 9 through 11, more practice like yesterday. 26, 27, and 28. They've given you a graph, and they want you to sketch the graph of the inverse. So here's what you do. You're going to pick 2 to 3 points, and then on those points, you're going to switch the coordinates. So we'll do number 27 together, and then I'll let you try 26 and 28 on your own. In number 27, this graph has this point, which is 0, 1. This point, 1, 2. And this point, which is that 2, 5?
Yeah.
Okay, we are going to find the inverse of these points. That means switch the coordinates. 0, 1 will become 1, 0. 1, 2 will become 2, 1. 2, 5 will become 5, 2. You just switch the x coordinate and the y coordinate. So when we graph it, 1, 0, 2, 1, and 5, 2. The dashed line just kind of shows you, like, if you were to fold this, those two things should match up perfectly. But the black line is the original function, and the blue one that I just drew in is the inverse function. And you get that by picking out some points, switching the x and y, and then plotting them.